run the job on the cloud resources like Amazon server, Google server, and you can download a result from these cloud resources. So these are three major partners that we are representing in India. So today we have scheduled this presentation and demonstration on this Nano Academic technology and its product. So I will focus on this Nano Academic technology. So if we talk about the company overview, so this company was founded in 2008 by Professor Hongo, Dr. Zhu, and Dr. Lee from McGill University. Basically, it was developed for molecular quantum transport that has been used around more than 10 plus years. And they enhance their feature for material development through advanced digitalization and modeling tools. Now they have also addressed the emerging sector of quantum computing revolution, that is QTCAD, basically a TCAD software based on the FEM method so that you can study spin qubit devices in semiconductor. So we have several unique features and more development are released day by day. Basically, they are located in Montreal, Quebec, Canada from McGill University. So this is the company overview. And if we talk about the journey of the software, like from where the journal was started. So basically in 2001 from McGill University, where Professor Taylor and Professor Hongo, who developed the quantum transport package first, which is also supported by some Northwestern University in 2002. So after several development, they have built this foundation of nano academic technology in 2008. And they have developed this NanoDCAL software in 2009. They have also developed this rescue software in 2015. So basically both NanoDCAL and rescue are the two main brand of material and device simulation tools. So these are the background simulation engine that will help you to run the simulation. So if we talk about this NanoDCAL software, so this NanoDCAL is a atomistic quantum transport software based on the DFT plus NEGF method. So that you can simulate any material and any device structure. And if we talk about this rescue software, so this rescue is dedicated for the material simulation. So based on the density function theory and density function perturbation theory, you can study any materials. So these are the background simulation engine. So apart from this background simulation engine, here you can see the graphical user interface is there. So this is the device studio, that is basically a graphical user interface of the NanoDCAL and rescue software. That will help you to do the modification. You can do the manipulation in your atomic structure, crystal structure, molecular structure, and device structure. So there is no need to write any script for any structure. Simply you can create the structure, define your parameter, and then this software will automatically generate their input file. So this graphical user interface is very easy to use. And even they have launched this NanoDCAL Plus and Rescue Plus for the advanced application. So this is the journey of the software. So this is the general overview of our tools. Basically both Rescue and NanoDCAL are the two main broad range of material and device simulation. So they include a broad range of advanced method for simulating complex material property at different level. Also, they have the tool and toolboxes that can be used to effectively preparing the calculation, executing the calculation, analyzing the result that comes out from the atomistic simulator. So this is the general overview. Now this NanoDCAL is very straight apart, general purpose, first principle quantum transport package, which combine both density function theory and non-equilibrium green function theory. So this software is written in MATLAB and C, and this software is used in lot of publication papers and good journal. So you can find on the Google Scholar page where many of the paper published in many domains like spintronics, battery and energy storage device, insulator, photocurrent, molecular electronics domain, and it cover all the applications. So it can focus on electronics property as well as quantum transport spintronics, including IV curve, field effect, dielectric effect, spintronics like collinear spin, non-collinear spin, spin orbit coupling, and it include all the common analysis tools like density of state, projected density of state, local density of state, projected local density of state, band structure, complex band structure, thermal transport tools, and Funan tools. So this all feature will be there. So you can model the structure very easily. Here you can see these are the some publication papers that is published by using this NanoDCAL software. And you can see this is the two probe device structure where we have the left electrode, right electrode, and center region. So not only the left and right, you can also define the front electrode, back electrode, top electrode, and bottom electrode. So up to 6 probe device structure, you can easily simulate with the help of NanoDCAL software. Now, if we talk about the bigger application of this software, so the bigger application of this software for the molecular structure simulation, molecular based device structure simulation, surface simulation, 2D material based device structure simulation, complex material like hexagonal, tetragonal, tri-black phosphorus material, interface between different geometry and different symmetry, and some carbon based material you can also study. Like we have the graphical user interface where we have the molecule 2D builder and also we have the molecule 3D builder. So that you can design your molecule, either it could be organic molecule or inorganic molecule. You can also create this surface so that we have the Miller indices like ESKL value you can define like 100, 110, 111. So whatever the combination you want to create, just you can define so that you can create the surface structure. So these are the bigger application where you can utilize our both NanoDCAL and Rescue software. Now this advanced tool are there for building the structure. You can build a crystal structure, molecular structure, device structure, and manipulate these properties. So you can manipulate the Brebes lattice parameter, alpha, beta, gamma value, ABC value, primitive cell, conventional cell, even armchair, zigzag, type of graphene, nano ribbon, nano wire, grain boundary. So different tools are there that will help you to build your structure. So this advanced tool are there for building the structure along with the user-friendly interface. So that you can define your DFT parameter, NEJF parameter, like electron temperature, cutoff energy, exchange correlation function like LDA, GGA. You can also define the iteration control, spintronics application, spin up, spin down calculation. So that all will be required for your input parameter. So once you define the parameter and you can do the simulation, then you can get some result. And that result you can visualize from our visualizer either in 3D view, 2D view, and 1D view. Here you can see these are the some material properties that you can study. Like you can study the electronics properties, structural properties, optical properties, thermal properties, magnetic properties, electronics and thermal transport properties, electron phonon coupling. So these are the material properties. So apart from the material, you can also study the device properties like IV curve, photocurrent, thermoelectric current, conductance, Seebeck coefficient, transmission spectrum. So that I will show you during the live demonstration. Now this nanodical can also work on spintronics domain apart from the semiconductor, material science, graphene, and other 1D and 2D materials. So it can work for the spintronics application, for the next generation nanoelectronics and device configuration, for the lower power consumption, higher density, that will increase your device performance. So not only the spintronics application, it can also work for the battery, energy storage device, photocurrent calculation, spin movement, spin up, spin down calculation, nano ribbon, and other different kind of structure can be simulated. So you can also rotate your tube at any angle. You can also define the polarization like rho, theta, and phi. So these are the spintronics application. And this nanodical can also work on photogalvanic spintronics application. You can design a multiple layer structure like mono layer, bi-layer, tri-layer. So multiple layer structure you can design. Here you can see this is the 3-layer structure where the graphene is sandwiched between two boron nitride. So these are the different materials where we have the left electrode, right electrode, and center region. So this center region is also called scattering transport region. So not only the left and right, you can also define the top electrode, back electrode, front electrode. Also you can define the anode, cathode. You can also define the gate terminal. You can also define the magnetic moment at different edge atoms. You can see this is the stagger potential that is produced by two boron nitride. So in this two boron nitride, we have defined the spintronics application, that is collinear spin, so that we can get the potential for the spin up and spin down. So apart from that, this nanodical can also work on semiconductor device application, molecular based device structure. So you can see this is the device structure where the gate voltage is applied. So this is the gate, this is the source, and this is the drain. So based on the gate voltage, you can find the IDVD characteristics, IGBG characteristics, transmission spectrum, conductance, Seebeck coefficient, photocurrent, and many more device property you can study. You can see this is the publication papers and this is the DI number. So this is the 2-pro device structure where we have the graphene left electrode, right electrode, and in the center region, you can see this is the molecule. So this is the 2-pro molecular based device structure. And for this device structure, we have simulated that transmission spectrum. So this nanodical can also work on mesoscopic electronic transport in two-state bilayer graphene structure. Suppose if you want to work on two-state graphene layer, like you can see, if you have a planar sheet and that planar sheet you want to twist at any particular angle, particular radius. So we have the angle position. So whatever the position you want to select, either left side, right side, so you can select that materials and you can rotate at any angle. And based on the angle, you can find the EK diagram, transmission coefficient, and many more properties while rotating and twisting the sheet. So you can also work on 4 terminal devices, 2 terminal devices, nano ribbon, nano wire, grain boundary, surface structure, crystal structure, molecular based device structure. So you can see this is the 4 probe device structure where we have the left electrode, right electrode, top electrode, and bottom electrode. So not only the 4 probe device structure, up to 6 probe device structure you can easily simulate. And based on the device structure, you can calculate their many more properties like their IDVD characteristics, their IV curve, transmission spectrum, photocurrent, Seebeck coefficient, density of state, their potential, stagger potential. So many more device properties you can simulate. Similarly, you can rotate a tube at any angle, at any particular radius, and based on the rotation, how much will be the defect in your sheet, a tube that you can also study. So if we talk about why this Nano Academy technology software is world class, so basically they are a team of nanoelectronics, physics, applied computing physicists, and expert developing atomistic and quantum simulation tool for the advanced application. So just a few words about the features and characteristics of our tools. Our tool include pretty unique features, atomistic and quantum transport features. We can predict the material properties, and as you know, the material properties like physics property of the material that will reduce the project time frame and accelerate the time to market, which is very important for the research and development. We also offer the fast converging tools with the advanced algorithm, and we also offer the powerful features including machine learning tools in our new version. So we offer efficient parallelism and scalable design in our course. So in our website, there are plenty of tutorials are there. So that will help the user to get started and get proficient quickly. And to enhance the user experience, we offer the user graphical user interface, such as Python API in the new version. We also enable the integration of third-party tools for plotting and displaying the curve. For the rest, yes, notably, we offer a free 1 year service for the advanced technical support of our tools. So if we talk about the product, so this Nano Academy technology developed three product. First one is NanoDCAL, that is basically for the atomistic quantum transport simulation. So based on the DFT and NEGF method, you can simulate any material and any device structure. So they have also developed this rescue software that is dedicated for the material simulation. So based on the density function theory and density function perturbation theory, you can simulate any complex material. They have also developed this QTCAT software that is basically for the quantum technology spin qubit devices in semiconductor. So this is my contact details. So for future requirement, any technical support, you can let us know so that we are ready to help you in your research. So thank you for listening this presentation. Now I would like to switch on the demonstration part. So you can see this is my C drive, and you can see this is my device studio folder. So I would like to open this folder, and my software is located inside this bin folder. You can see this is the device studio application file. So I would like to open this file. So once you open this file, you will get this interface. So here you can see this is for creating a new project. Either you can open your existing project. So I would like to start from the scratch. So create a new project. And then you can select this OK. Here you can enter the project name. You can see I would like to select the project name. You can select the location where you want to save this project and then select this save option. Now you can see this is my project name. So this is the project explorer where the input and output file will be shown. This is the property explorer where the property of a whole structure or individual atom you can see. And this is the job manager. You can see these are the different toolbar and these are the different menu bar. So first I would like to select this file option. And in the file you can see this is for creating a new project. You can open your existing project. You can save the project. And here you can design a new device structure, crystal structure, and molecule structure. And you can see this is the import option. So this software have two options to import the material. Either you can import the material from this local database that exists inside the software. You can also import the material from the online database. So if you talk about this import local, you can see C drive, device studio folder, and you can see this is the material folder. And in this material folder, you can see we have 0D material, 1D material, 2D material, 3D material, and some organic materials. So this is the 0D material. In 0D material, you can see we have the molecules. Like you can see, we have the amorphous and crystalline molecule. So these are the amorphous molecule. And you can see this is the crystalline molecule. So this is the 0D material. You can see this is the 1D material. In 1D material, you can see we have the nanotube. So these are the different combination of crawl vector, like either armchair, zigzag, any nanotube you can select and then select this open so that you can easily import the material in our device studio. So this is the 1D material. This is the 2D material. In 2D material, you can see we have the novelty material like arsenic, bismuth, black phosphorus, hexagonal boron nitride, and also we have the graphene. So this is the 2D material, and here you can see this is the 3D materials. In 3D material, you can see we have the conductor, insulator, layer material, magnetic material, metal oxide, novelty material, and semiconductor. So these are the 3D materials. You can see this is the conductor, and these are the pure metals. So these are the conductors. You can see these are the insulators. This is the layer material. This is the magnetic material. You can see this is the metal oxide. So these are the metal oxide. This is the novelty material. In novelty material, you can see we have the perovskite based material. So these are the perovskite based material. You can see this is the topological insulator. And here you can see this is the valley half metals. So this is the novelty material. And you can see this is the semiconductor. So this is the 3D materials. And you can see this is the organic material. In organic, you can see we have the crystal and molecules. So now the conclusion is that this is the material database that exists inside this software. So once you install the software, you will get these materials. And here you can see this software support this file format like .sjw file format, xyz, .cif, .xsd postcard, content, scf.input file. So these file format you can easily import in our device studio. And then you can study their many more properties by NanoDCAL and the rescue software. So either you can import the material from this local database, and if the material is not available, then you can also import the material from the online database. You can see this is the import online option. So this is the import online. Here you can enter the chemical formula of the material, and then you can click on the search option. So from this crystallography open source database, it will search the material, and then you can select from this add option. So here you can see I would like to import select some materials. You can see this is the chemical formula of this molybdenum sulfide, and I would like to click on this search option. Then it will search every possible combination of molybdenum and sulfur. So you can see these are the different combination with different space group information. So you can see this is the MO2S4. So these are the different structure. So as per your need, you can select the structure and then click on this add option. And also you can see this is the material MO2S4, and here you can see this is the symmetry information like their lattice parameter, like this is the ABC value, alpha beta gamma value. Here you can see these are the atoms and their Cartesian coordinate point. So any material as per your need you can select and then select this add option. Now you can see this CMO2S4 has been imported in our device studio. And if the material is not available, either in import local option, either import online, then you can also create your own material. So if you want to create any material, here you can see this is the crystal builder that will help you to build your crystal. So this is the crystal builder interface that will help you to build your crystal, either simple structure, complex structure, alloy, any crystal you can create. You can see these are the lattice information. Like we have the space group. So these are the various space group information. And based on the space group, it will automatically select their Brebes lattice. You can also change the ABC value, alpha, beta, gamma value. You can add any element from this add option, and then you can define their fractional coordinate point P1, P2, and P3. So once you design the structure, here you can see this is the preview style. Like you can show their primitive cell, either conventional cell. Suppose if you want to create a gold-based crystal structure, so for the gold, I would like to select their face and space group information. That will be face center cubic structure. So you can see this is the face center cubic structure, and here you can change the ABC value. So as per your research work, you can change. Here I would like to take a default value that will be 4.007. You can see this is the 4.07 angstrom, and then you can add the element. Here you can see this is the add option. You can select any fractional coordinate point. I would like to select this 0, 0, 0. And you can see this default carbon atoms has been selected. So if you want to change this element, you need to double click, then the periodic table will be open. And from this periodic table, you can select any element. You can see this is the gold that has been selected. I would like to select this OK. So once you select this OK, then this carbon element will be replaced by the gold. You can see carbon has been replaced by the gold element. So n number of element you can add from this add option like that, and also you can change their fractional coordinate point. You can also delete any element. So once you design this structure, you can go to the preview style. You can see this is the primitive cell. You need to select this preview. You can see this is the gold primitive cell structure. And if you want to show the conventional, so you can see this is the conventional cell. Select this preview. So this is the gold based face center cubic structure conventional cell. So for creating the new crystal structure, you should know their space group information, their ABC value, the element, and then you need to select this preview, and then you can go for the build option. You can see this is the face center cubic structure of the gold that I have created from this crystal builder. And if we talk about this molecule builder and device builder, so you can see this is the device builder. So up to 6 pro device structure you can build. Like you can build the left right device structure, left center right device structure, bottom and top device structure, bottom center and top device structure, front and back device structure, front, center and back device structure. So any combination you can select. Here you can see this is the left, center, right device structure. You need to select this okay. And then you can define the materials for the left electrode, center region, and then for the right electrode. So this is the basic device in structure. And if you talk about the advanced builder, you can see you need to import the materials for the left electrode, center, and right electrode. And then you can define the surface vector. So before building any device structure, first we need to import the material so that we can define the left electrode, center, and right electrode. And if we talk about the molecule builder, so you can see this is the builder, and here we have the molecule 3D builder, and this is the molecule 2D builder. So if we talk about this molecule 2D, so this is the molecule 2D builder interface. In the left hand side, you can see these are the various fragmentation, and you can see these are the various toolbar. So as per your need, you can design your device structure. So any complex structure you can design. Like you can see, this is the ring segment that I have selected. If you want to draw the single bond, you can see. So if you want to design any structure, so as per your need, you can select the fragmentation, and you can see these are the various bonding option. Like you can see this is the draw single, double bond, triple bond. So if you want to select this draw single, you can see this draw single has been selected, and you can draw the single bond at every side of the carbon element. So basically, I am going to create a benzene structure. So for the benzene structure, we need C6 and H6. So we need to replace all the CS3 with the hydrogen element. So if you want to replace, here you can see this is the choose element. And from this periodic table, you can select any element. So I would like to select this hydrogen. You can cancel the periodic table, and you can replace all the CS3 with the hydrogen element, so that it will become C6 S6 benzene molecule. So any complex structure you can design, and then you can select this apply data. You can see this is the benzene molecule. In the toolbar, you can see this is the force field calculation, so that you can minimize your structure. Like we have the UFF, GFF, GMTL. So as per your need, you can select the force field calculation, and you can minimize your structure. So here you can see in this structure we have 12 atoms, and this is the chemical formula C6S6. And if we talk about this molecule 3D builder, so you can see this is the molecule 3D builder, and here you can see this is the add atom option. So if you want to select this one, then the periodic table will be open. You can see this is the carbon element, and there are various fragmentation. Like you can see single atoms. This is the divalent. So these are the various fragmentation for this carbon element. And if you want to show any fragmentation, you need to select. You can see this is the tetrahedral. And if you want to add this structure, in this dashboard you need to click. Here you can see these are the biomolecules. So biological molecule you can also select. You can see this is the structure. So simulation of the biomolecule is also possible from this NanoDCAL software. And here you can see this is the R groups fragmentation that will help you to design your molecule. And you can see this is the ring segment. You can see this is the benzene. This is the benzene structure. So any structure you can select. You can see this is the fluorines. And then you can click anywhere. So once you design this structure, you can select this apply data. So this is the material that I have imported from our import online option. I have created a new crystal structure. I have created this benzene structure from the molecule 3D builder, 2D builder, and this is the molecule that I have created from the molecule 3D builders. Suppose if you want to do the simulation for any materials, you can see this is the MO2S4. If you want to select only single monolayer structure, I would like to delete this one. You can see the atom has been selected, and select this delete option. Now you can see this is the monolayer EMOS2 crystal structure. In this structure, you can see these are the properties. This is the vector value, vector A, vector B, vector C. We have 3 atoms, total area of this lattice, and this is the chemical formula, MOPS2. We can also rename this one. And if we talk about the simulation, so for this simulation, you can see we have the simulator. And here you can see this is the NanoDCAL software. That is basically for the atomistic quantum transport simulation. Based on the DFT plus NEGF method, you can simulate any materials and any device structure. So basically DFT will apply for the materials and DFT plus NEGF will apply for the device structure. We have the rescue software that is dedicated for the material simulation. And also you can see our software support the interface with the WASP, LAMPS, Ovito, Quantum Espresso, Gaussian, and Newton. So their input file you can create. So I would like to select this NanoDCAL. And in the NanoDCAL, you can see multiple options are there. You can see this is the virtual crystal approximation that will require basically for the doping. So you can see this is the VCA calculation. You can see this is the element. Either you can select this molybdenum or you can select this sulfur. This is the basis pseudo potential database, LDA double zeta polarized. This is the doping type. You can see this is the P type, and also we have the EN type. And also you can define their value. So doping value you can define. So this is basically for the mixture vacancy. And if we talk about the mixture atoms, you can say this is the mixture atom. So you can mix any atoms in this structure. If we talk about adding any atoms, you can see this is the add option. And this default carbon element will be selected. We need to change with any other element. Like you can see this is the silicon doping. And then you can define their composition value. So n number of atom you can replace and their composition value should be 1. So in this structure, it will become 0.75% molybdenum and 0.25% silicon element. So 0.25% molybdenum will be replaced by the silicon element. And then you can generate their file. So this is the VCA that is required for the doping. And here you can see this is the self-consistent field calculation. So here you can define your DFT parameters. And before this DFT parameter, if you want to optimize your structure, either material, either device, then you can select this relax option. So this relaxation is basically for optimizing the structure. Here you can see this is the relax method. We have the molecular dynamic and we have the conjugate gradient. So in this software, we have two methods, molecular dynamic and conjugate gradient. So any method as per your need you can select and then you can generate their input file. So this relax is basically for optimizing. So I would like to first define their DFT parameters. You can see this is the self-consistent field calculation for this crystal. So this is the basic settings that we need to define. Like we need to define the electron temperature in the unit of Kelvin. We need to define the cutoff energy in the unit of RT, Rydberg, electron volt. You can also define the exchange correlation function, LDA, GGA, and then K-point sampling. that we need to define, like density matrix, Hamiltonian matrix, and total energy. And you can see this is the maximum iteration step. This is the basis set. Like this is the arrangement by element or by atoms. You can see these are the atoms. So in this structure, we have two atoms, molybdenum and sulfur. And here you can see their pseudo-potential database. You can also change this pseudo-potential from this PVW polarized. A user-defined database is also there. You can see this is my device studio. Here you can see we have the neutral atomic database. Here you can see this is the general information for every atoms, like they're double zeta polarized, single zeta polarized. These are the lanthanide series. This is for its specific element. You can see silver double zeta polarized, silver single zeta polarized. You can also import your file. And here you can see this is the LDA plus U. That is basically for the Howard atoms. Howard in the sense you can define some SPDF combination. And here you can see this is the spin type. So that is basically required for the spin tronics application. Suppose if you want to define the spin like no spin, collinear spin, and general spin. If you select this collinear spin, you can see these are the element and their spin polarization row value. And if you talk about this general spin, you can see these are the element and their spin polarization rho, theta, and phi. You can also change their value. Like you can change the rho value from 0 to 1, theta from 0 to 180, and phi from 0 to 360. And this is the spin orbital interaction. So I would like to select this no spin. So whatever the parameter you want to enter, you can define and then click on this generate file. So once you define the parameter, click on generate file, then this software will automatically generate their input file. So there is no need to write any script. Simply define the parameter and click on generate file. And here you can see this is the script for this MOS2 materials. You can see this is the HCF calculation. This is the basic settings where we have defined the electron temperature, cutoff energy, exchange correlation potential, K point sampling. No spin is included. This is the iteration control parameters. This is the basis set where we have the atoms, their pseudopotential database, and their XYZ Cartesian coordinate point. So this is the script for this structure. And if you want to run this job, you need to select the file, right click, select this run option. You can also run this job on parallel, suppose 5 core, 10 core, 15 core. So there is no limitation of core. You can define up to 128 core. In my computer, you can see I have 12 core. Then you can select this run option to run this job. Now you can see this is the sf.input file that is in the running condition. So in the meantime, if we talk about the analysis parameter for any materials, you can see this is the simulator, NanoDCAL, and here you can see this is the analysis. So these are the material analysis parameter that user can study. Like you can study the density of state, effective potential, total energy, band structure, charge, Hessian matrix, phonon band structure, electron density, potential, transmission channel, eigenstate, full band structure, effective mass, complex band structure, JT that will require for the thermoelectric application, Hunan full band structure, Hunan density of state, Hunan transmission channel, modulus like Young modulus, elastic modulus, atomic force, and stress. So whatever the parameter you want to study, you need to double click, then it will be selected. You can see this is the density of state and their parameters. Like we have the K-point sampling, number of energy point, energy range, and this is the projection. Projection in this sense, you can see this is the default none option, atoms, orbitals, and this is the ELL. So whenever you select the atom and orbital, then your density of state will be plotted with the atom and orbital wise. And if you select this ELL option, then your density of state will be plotted with orbital with angular momentum. And also you can see this is the local density of state. Here you can select the regions and point. So I would like to select this density of state. Here I would like to default K-point sampling so that we can get the plot. So this is the density of state. And if we talk about the band structure, you can see this is the band structure parameters. You can see this is the symmetry K point. And this is the number of K point. If we talk about this Brillouin zone path, so you can see this is the Brillouin zone path for this MOS2 materials. You can see this is the symmetry K point. If you want to change any symmetry point, you can see either you can add, you can also change their value. And you can also delete. So this is the band structure. And if you talk about this electron density, you can see this is the watt density. Like we have the charge density, total electron density, row density, bond density, redistributed. So these are the multiple densities. So as per your need, you need to select. You can see this is the potential. You can see this is the watt potential. We have the effective potential, Hartree potential, exchange correlation, and this is the neutral atom potential. Like you can see this is the Hartree potential. This is the transmission channel. This is the eigenstate that will require for the visualization of LUMO and HOMO. Here you can define the K space point, then number of band. If you want to calculate this phonon band structure and ZT, before that you need to select this Hessian. So Hessian matrix you need to simulate. Then you can go for the Funan and then ZT. You can see this is the Funan band structure. So any parameter you can select, define their parameters, click on generate file. Now you can see the input file has been generated. Here you can see the sf.input file has been completed. Now we need to run this analysis input file so that we can get the output. Like you can see, this is the density of state that I would like to run. Band structure, electron density, potential, transmission channel, eigenstate, Hessian matrix, and this is the Funan band structure. So you can see in the queue condition, I have run all this input file. Like when this input file will be completed, then this input file will start automatically. So in the queue condition, you can run multiple input file. And once the input file will be completed, then you will get the output. Here you can see density of state completed and their output file has been generated. And if we talk about the background simulation, so you can open this log file. And you can see first it will load the pseudo potential database. You can see this is the periodic 2D materials. No spin is defined. We have 3 atoms, total electrons, and you can see this is the step-wise step procedure. You can see the timing, raw matrix, hybrid matrix, total energy, band energy, grid charge, and orbital charge. And you can see it has taken 37 seconds for the SCF simulation. You can see this is the density of state. With the help of wave function method, it will simulate the density of state. You can see it has taken 4 seconds for 3 atoms. Band structure simulation, it has taken 1 second. And if we talk about the output file, so you can see this is the density of state.xml output file. If you want to show the graph, first you need to select the file, right click, select the, you can see this is the density of state with respect to energy for the MOS2 materials. In the center region, you can see we have the Fermi energy. You can also export this raw data. You can see this is the export option. Here you can select the format, either PNG, JPG, BMP, PDF, TIFF format, EPS format, and text format. So as per your need, you can select and then select this save option so that you can easily export your raw data. So this is the density of state. Here you can see this is the band structure. And in this band structure, we have defined no spin. You can see this is the conduction band. This is the valence band. And here we have the Fermi energy. So these energy are in the electron volt. And here you can see this is the symmetry K point. This is the total electron density, 3D view. You can see this is the 2D view. Total electron density along x-axis, y-axis, and z-axis. So 3D, 2D, either 1D view, you can plot. You can see this is the 1D view of total electron density in xy plane, yz plane, and xz plane. Here you can see this is the Coulomb potential, 3D view, 2D view, along x-axis, y-axis, z-axis, and this is the 1D view. Along xy plane, yz plane, and xz plane. This is the transmission channel with respect to energy. And here you can see we have the channel number. So these are the material properties. You can see this is the Eigen state, 3D view, 2D view, and 1D view. And this is the phonon band structure. So these are the material properties. So if you want to create any device structure, so here I would like to import some material so that we can define the left electrode, right electrode, and then center region. So you can see I would like to select this gold, select this open. So this is the gold material that I would like to select as a left electrode, right electrode, and center region. So you can see this is the simple structure. If you want to show their face center cubic structure, either body center cubic structure, you can see this is the redefined crystal. You can also create structure. You can also create graphene nano ribbon, nanotube, grain boundary, nanotube structure, nanowire, decided graphene-like structure, decided zinc blend-like structure, icosahedron, cubectohedron, and well cluster. So these are the builder. So for the face center cubic structure and body center cubic structure, I would like to select this redefined crystal. And you can see this is the redefined crystal by expressing the new cell vector UVW as a linear combination of ABC. This is the face center cubic structure and this is the body center cubic structure. You can see this is the face center cubic structure of this gold atoms. And if you want to make a supercell, so for this supercell, I would like to select this build option, select redefine crystal, and you can make the supercell in any direction, either direction A, direction B, and direction C. So you can see 2 times in the A direction, 2 times in the B direction, and 4 times in the transport direction. And now you can see this is the supercell structure. So this is the supercell structure ZX view. If you want to show the XY view, you can see this is the 3D viewer. And here we have the XY view. So your desired structure you can create from this device studio. Suppose if you want to delete these items, you need to select this delete option. If you want to select more items, you can select and then you can delete. So this is the XY view. If you want to show the ZX view, you need to select this 3D viewer and you can see this is the ZX view. If you want to delete some more items, so you can see this is my desired left electrode structure. If you want to create a right electrode, so if you want to create a same right electrode, you need to select and you can see this is the mirror atom. So for the same structure, you need to select, go to the mirror atoms. You can define the normal vector and the distance between the electrode. I would like to select this XY direction and the distance between the electrode are 5 angstrom. You can enable this copy option. Then you can select this apply. Now you can see this is our left electrode, this is our right electrode, and in center region, I would include some molecules. So if you want to show all the atoms inside the same unit cell, so we need to increase some vacuum energy in the transport direction. So if you want to include the vacuum energy, you need to select this convert to crystal. You can also change the lattice. Here you can see this is the Bravais lattice, simple structure, face centered, body center, rhombohedral, hexagonal, tetragonal, tetragonal body center, orthorhombic, orthorhombic for the body, face, and base centered. You can see this is the monoclinic, monoclinic for the base centered, and triclinic. And if you want to increase the vacuum energy, you can see this is the direction A vacuum energy. I would like to change. This is the vacuum energy for the direction B. And here I would include the vacuum energy for the transport direction. And you can see every atom inside the same unit cell. If you want to show this structure in center region, here you can see this is the center option, like center along A, center along B, and center along C. So in any direction you can select and make it centrally fit. So you can see this is in the center position. If you want to include some molecules in the center region, either you can create a molecule from this molecule 3D and 2D builder. You can also import the molecule from this import local option. You can see these are the molecules. If you want to include this alkenyl molecules, you can see this is the alkenyl molecules. And if you want to add this molecular structure in this device, I would like to select the atoms, Control C, so that it will be copied. And here you can Control V. You can see this is our molecules. So if you want to show this structure into center, you need to select the center option. Now you can see the atom has been connected. You can see these are the gold atoms. This is the sulfur atoms. And this is the gold element. And if you want to convert this structure into device, so you can see this is the convert to device option. And here you can define the electrode. So based on your device structure, you need to select the electrode, either left electrode, right electrode, bottom electrode, top electrode, front electrode, and back electrode. So in this device structure, only two electrode is possible, left electrode and right electrode. I would like to select this left electrode, right electrode, select this preview. You can see this is the left electrode, right electrode, and this is the center region. If you want to change the electrode region, here you can increase the value like minus 8 angstrom, 8 angstrom, and you can see this is the gate, left electrode, right electrode, and center. So this is the two probe device structure where we have the electrode and center region. So if you want to simulate this device structure, you can see simulator, NanoDCAL, and you can see all the options are enabled, like the self-consistent field calculation, the optimization, transistor option, IV curve. So this is the self-consistent field calculation for the device. This is the basic settings, contour integral, electrode, you can see electron temperature, electrode voltage, K point for the left electrode, and electron temperature, electrode voltage, and K point for the right electrode. So here you can define the voltage. This is the iteration control parameters, basis set. Here you can see this is the doping. So doping you can also include. So once you define the parameters, select this generate file, then it will generate 3 input file. The input file for the left electrode, right electrode, and for center region. So DFT apply on the left electrode and right electrode, and DFT plus NEGF will apply in the center region. And first, we need to run the electrode input file, because this device will take the output from the left electrode and right electrode. You can see it will take the output from the left electrode and right electrode. So before running this scf.input file, first we need to run the scf.input file of the left electrode and right electrode. And if we talk about the analysis parameter for the device, you can see these are the analysis parameter for the device, like density of state, effective potential, total energy, scattering state, transmission spectrum, photocurrent, IV curve, charge, electron density, potential, conductance, Seebeck coefficient, thermoelectric current, and AC conductance. Like you can see, this is the IV curve. Here we can define the K point sampling. This is for the photocurrent. We need to define the polarization basis, polarization vector, linear polarization, left circulary, right circulary, elliptical polarization, and oblique elliptical polarization. and their theta and phi value. We also need to define the photon energy range, K point sampling, and you can irradiate atoms. Suppose if you want to fall the light on the center part, so center part atomic indices you need to select. You can see the atomic indices has been selected, and in that region the light will be fall. So that you can calculate the photocurrent. You can see this is the thermoelectric current. You can define the K point sampling and temperature. This is the conductance. So any parameter you can select and then select this generate file. And you can see in this structure we have 76 atoms. So it will take some time to simulate this structure. So I have simulated some project that I will show you. So this is the device builder that you can create a device structure. So basically this is the two-probe device structure where we have the electrode and center region. If you want to convert this structure into transistor, you need to select this simulator, NanoDCAL, and here you can see this is the transistor. You can see this is the gate parameters. We need to define the spatial region, dielectric permittivity, and oxide thickness. You can see this is the oxide thickness. This is the gate. This is the drain, and this is the source. You can see our source is at the right side. So source, drain, and gate. Here you can define the gate voltage, any value you can define. You can define the gate type, either bottom and top, either front and back. You can define the gate regions, then transistor option. You can define the source, either left side, either right side, and then the biasing voltage. So that you can calculate the IDVD characteristics and IGVG characteristics. So based on the gate voltage, you can find that. So this is the transistor builder. And if we talk about this graphene nano ribbons, so you can see this is the nano ribbon builder. Here you can define the crawl vector, E and EM value. You also define the bond length. Select this preview. So you can see this is the 2x2 zigzag graphene nano ribbon. And if you want to do the passivation with the hydrogen atoms, you can see the passivation has been enabled. And here you can see this is the hydrogen passivation. So this is the zigzag structure. If you want to create an armchair structure, then you can define M is equal to 0. And you can see this is the armchair structure. So this is the graphene nano ribbon. If you want to create any other nano ribbons, then you need to change the site items. Like you can see this is the boron, and here I would like to select the nitrogen. Then it will create boron nitride base nano ribbons. You can see this is the boron nitride base zigzag nano ribbons. So any nano ribbons you can create. And if you want to increase the length, you need to select this redefine crystal, and here you can redefine in transport direction. So this is the single layer. If you want to create a multiple layer, you need to copy, you need to select, go to the mirror atoms. Here you can define the normal vector, you can define the distance between the layers, and then copy, then apply. So you can see this is the two layer. So multiple layer structure you can create. So this is the nano ribbons. You can also create a nanotube. You can see this is the 8 by 8 nanotube structure. Similarly, if you want to create any other nanotube, then you need to replace the atoms. And similarly, if you want to increase the length, you need to select this redefine crystal. So here you can see these are the different builder. You can also calculate the distance. You can also calculate the bond angle. You can also calculate the dihedral angle measurement. You can also measure the vector value. So these are the different toolbars. So if I open some existing project that I have simulated for the device structure, so you can see this is the device structure that I have simulated. You can see this is the hydrogen passivation. And in this structure, you can see I have defined the spintronics application, which is collinear spin. You can see these are the different analysis parameter for this device structure. Density of state for the spin up, for the spin down, and this is the both spin up and spin down. This is the transmission spectrum for the spin up, spin down, both, and total. This is the total electron density, and you can see this is the Seebeck coefficient for the device structure. Blue one is for the spin up, and red one is for the spin down. So this is the Seebeck coefficient with respect to temperature, and this is the Seebeck coefficient with respect to chemical potential energy. In the plot type, you can see this is the Seebeck coefficient, and this is the Seebeck spin and charge coefficient. And also this software is integrated into MATLAB. So you can also plot the graph in the MATLAB, and also you can do the simulation from the MATLAB. So if you are exporting, writing the command, so you can use the MATLAB. Or you can also create the structure from this device studio, and then you can also study from the simulator. And if we talk about the theory and background equation, so for the theories, you can visit our this nanoacademy.com. So this is our official website. Basically, for the FinFET technology, we have another software which is QTCAD. So atomic level simulation you can study from the NanoDCAL, and for the FinFET, GAFET, we have the QTCAD software. So you can see this is our official website, nanoacademy.com. You can see this is the document and tutorials. And these are the product, NanoDCAL. Then you will get the theory and tutorials. You can see this is the theory, DFT NanoDCAL, ENEGF DFT NanoDCAL, and this is the post analysis. You can see binary structure and their theory and equations are mentioned. So whenever you get the time, you can visit our website, so that I hope you will be more familiar about the product. And if we talk about the FinFET, we have the QTCAD software. So you can see from this browse option, I can import our project. So you can see this is my Device Studio project. And this is my Graphene Nano Ribbon. So this project, I would like to import into MATLAB. You can see these are the device. So either this way you can plot the graph, other Device Studio you can plot the graph. You can see I have defined different biasing voltage, and also I have simulated the current voltage curve. You can see this is the current voltage curve.mat file. Here we have defined the voltage 0, V2 0.4, and this is the I1 current and I2 current. So if we talk about the IV curve complete graph, then you can see I have taken the data from this simulated result, V1, V2, I1 total current, I1 for the spin up, I1 for the spin down, I2 total current, I2 spin up, spin down, and this is for plotting the graph. And I need to select this run option, then it will plot the graph. So this is the spin current. Because in the device structure, I have selected collinear spin. You can see this is the I2 total current, I2 for the spin up, I2 for the spin down, I1 for the spin down, spin up, and I1 total current. And if we talk about the photo current, you can see I have simulated the photo current. Photo current for the lead first and lead second. Because the device simulation will take some times. And if we talk about the transistor output file, you can see this structure I have taken as a transistor. So this is the silicon based transistor. And you can see I have simulated their IDVD characteristics. You can see IV curve plot is there. So a different drain voltage, gate voltage, I have simulated. And if we talk about the graph, So I need to select simulator, NanoDCAL, go to the transistor plot. And then you need to select your project location. You can see this is my project and this is my transistor folder. And you can see this is the IDVD characteristics at different gate voltage. So this is the IDVD. And if we talk about the IGVG, so you can see this is the IGVG characteristics. So I have shown you some maximum properties of this software. Because as you know, 2 hours is not full enough to show the full capability of the software. So if you have any specific queries, so you can either unmute the mic and either you can drop your query in the chat box so that I will try to help you. And for the FinFET technology, you can see I have the QTCAD software. So the QTCAD software. So you can see FinFET technology, you can select in the QTCAD. So if anyone has any query, so you can unmute your mic and ask me the queries so that I will try to help you. So if you have any questions, so you can ask. Yes, you can reduce or increase the band gap as per your need. So first you need to select any materials. And if we talk about the band gap value, you can see this MOS2 I have created in this device studio. So this is the project that I have created. And you can see I have selected this MOS2 and also I have created the band structure and their output file. And if we talk about the band gap value, so you can see this is the MOS2 folder, NanoDCAL crystal folder. And here you can see this is the band structure.mat file. So you can double click, then the file will be loaded, type the command data, then press the enter. And you can see this is the band gap value. So this band gap value are in the unit of Hrt. So if you want to convert this band gap value into electron volt, then you need to multiply by 27.54 something. Then you will get into the electron volt. So this is the band gap value. This is the top of the valence band value. This is the bottom of the conduction band. So in the image you can see here we have the electron volt. And in the data we have the Hrt energy. Yes, QTCAD is based on the finite element method. Basically, TCAD software for the spin qubit technology in semiconductor. Here you can see this is the QTCAD. You can see these are the some example. So you can see this is the GAFET, and this software comes with the Python interface. So you can see I would like to open my QTCAD Python interface, and I would like to import my file. You can see this is the QTCAD that I have already installed. In this QTCAD, we have three simulators, like device simulator, that is for arbitrary 1D and 2D structure, 3D, 1D, 2D, and 3D structure. And also we have the transport simulator, so that you can find the current flowing through the junction. And this is the qubit technology. Here you can see I have some examples and tutorials. You can see this is my GAFET, gate all around field effect transistor. So basically, you need to write the script in this visual code. You can see I have defined the device structure. I have defined the gate to source voltage, meter per function, length of the total device structure, their radius. I have also created the mesh file, mesh 3D geometry file. I can load the mesh. Through this graph, I can plot the mesh. In this device, we have selected FD approximation. And here you can see I have defined the channel oxide layer, that will be silicon dioxide, source oxide, silicon dioxide, drain oxide, silicon dioxide. And at the channel, source and drain, I have selected silicon materials. And also you can see I have defined the doping. I have created the boundary condition for the source, ohmic boundary condition. At the drain, I have created ohmic boundary condition. We have selected this Poisson solver so that we can create the electric potential through the junction, like electrons, holes, phi, conduction electron, conduction energy, valence energy. And through this Schrodinger solver, we can calculate the envelope function, like the eigen function for the ground state, first excited state, and second excited state. So if I run this, you can see first it will load the GMS 3D structure. You can see this is the GAFET mesh file. So this is the mesh file. Source, drain, and this is the gate all around field effect transistor. Then it will solve the Poisson equations. Poisson iteration, so that we can get the electric potential and also band energy. So you can see this is the electric potential along with the distance. This is the band diagram. Conduction energy, valence energy, and this is the Fermi energy. And you can see this is the eigen function for the phi. This is the ground state, first excited state, and second excited state. Here you can see this is the energy levels. So basically, CentOS and Silvaco are the micro level simulator and not for the qubit technology. So this qubit, and also in CentOS and Silvaco, there is some problem in the convergence. Like if you simulate below the 100 at Kelvin temperature, then your device structure will not converge. But in our software, you can convert the structure below 100 millikelvin temperature. And this is the world first qubit simulator. So this is the QTCAT for the world first quantum technology spin qubit simulator. So there is no software in the world. Okay, so for the videos, you can visit our YouTube channel. And also you can find some tutorials in this space. If you talk about this NanoDCAL, QTCAT, any product you can select, and then you can get the tutorials. So you can see step by step procedure are mentioned for simulating device structure. Here you can search impulse technology. So this is our official website. Here you can see this is the playlist. And in the playlist, you can see we have the videos for the device studio, graphical user interface. We have the QTCAD videos for the quantum technology. And also you can see this is the rescue software videos, Laos for the large scale PV module simulation. And this is the NanoDCAL software, set first, that is for the solar cell and OLEDs. And we have the exabyte. So any product you can select and then you will find their videos. So for this IDVD characteristics, you can see I have simulated. So first you need to create some device structure. You can see this device structure I have created. So you can create any device structure, go to the simulator, NanoDCAL, and you can see this is the transistor. So any parameter as per your need you can define, and then you can generate the input file. Here you can see the input file has been generated at different drain voltage and gate voltage. Then you need to run the input file, and then you will plot the graph. VD 0, drain is 0, drain is 0.2, gate is 0.1. You simulate, then go to the simulator, NanoDCAL, go to the transistor plot. In the transistor plot, you can see This is my complete device studio project. So that you need to select, go to the select folder. Then you will find the IDVD characteristics, and this is the IGVG characteristics.
Yeah, excuse me, sir.
Yes, ma'am.
Yeah, so what is the device you just showed now, sir? Now you explained what device is that actually, sir? It only
Like,
has source and gate. We have not done any doping. We don't have any gate.
ma'am, you can see this is the device structure that I have created. So
So
if you
what
want to
device is
convert,
it? Sir? What device is it?
so this
Like
is the
what?
silicon-based device structure. Silicon-based device structure.
What device, sir? It is like devices. We have many devices. Now, what transistor it is? Like either a MOSFET or a FinFET or a TFET, like that.
No, ma'am, this is the two pro device structure. And basically, if you want to select transistor, so you can see here, we will get the transistor option.
Okay, then
Here
how
we
do
have,
we do the doping? How do we add the gates, oxides?
here you can see, you can define the spatial region, dielectric permittivity. Then you can define the oxide thickness layer. You can see this is the oxide thickness. You can define the gate voltage, gate region. You can see this is the gate terminal.
Okay.
And here we have this drain, and this is the source. You can see our source is located at the right side. So this is our source, this is our drain, and this is the gate. And here I have defined the biasing voltage. So if you want to include the doping, so for the doping, you can see this is the basis set, and here this is the doping.
So how do I select the regions for doping?
Which one, ma'am?
How do I select the region for doping? For example,
Okay.
if I have to dope only
Yeah.
in the source, I have
Yes,
to dope
yes.
only in.
So you can see this is the, you need to enable this doping. Go to the search option, and where we want to, you can see this is our source doping that has been selected. Again, you can add one more search, and this is the drain.
Where do I give the doping concentration? How do I give the doping concentration? With what concentration I'm doping?
So for that, you need to select particular. If you want to define the concentration, then this is the VCA, virtual crystal approximation. Here you can define the mixture atoms. You can select any atoms and their composition.
Sir, it will be helpful if you show us how to design a basic silicon MOSFET here, like with different doping concentrations and all. Because if you're showing like this, now we don't have a flow to understand. So
Once again, so I need to create a new project. Oh,
yeah,
wait.
if you just explain how to develop a basic silicon MOSFET structure, no?
So first, I need to import some silicon atoms. And I need to select as a face center. And then I would like to increase the length. So if you want to increase the length, you can see the length of this structure has been increased. And also I need to include some vacuum energy so that we can define the oxide thickness. So here I would like to define 10. Here 10 vacuum energy. I need to include 15s. And then I would make it centrally fit. So you can see this is my desired structure, and I need to convert this structure into device. First, you can create a two-probe device structure. You can see two-probe device structure, build option, and then go to the simulator, NanoDCAL, then create a transistor. You can see. You can define the dielectric permittivity. If you want to define the oxide thickness, so here you can enter that value. So you can see this is the oxide thickness. You can define the gate voltage, gate regions, and where you want to show the source. And if you want to include the doping, so for doping, first you need to generate the files. Like if you want to include the silicon dopings,
So when we convert it into a transistor, it will automatically get the gate and the oxides.
yes,
But we
yes,
don't
yes.
need to specifically again draw them or design them.
No, no, no need to define.
Okay, for
Similarly,
example, if I have to take a multi-gate, for example, double gate MOSFET or something like that, then how will I design it?
ma'am, in this NanoDCAL device studio, a single gate you can define. If you
Oh, we
want to
cannot
define
define
more gate,
multi-gates.
so for this multi-gate, we have the QTCAD software.
For multi-gate?
So any gate terminal you can define in QTCAD software. But at a single gate, you can define in device studio.
Okay, okay. So we cannot design FinFET in this
No,
because
FinFET
FinFET we
is,
need to.
yes, FinFET basically you can define in QTCAD.
Okay, okay,
You can see this is the QTCAD workflow, and here we can select the FinFET technology.
okay.
And this is the FEM based simulation, not for the atomistic simulation.
So you will
So
be
if you
giving
want
a
to do
demo
the,
for that also, no?
yes, we can arrange. So, and also you can see there are some videos are there for this quantum technology.
Yeah,
If you want
because
to
the
show the
main
demo,
purpose for us is to design the multi-gate FETs. That is the reason. We do like as of now we are not working on MOSFET. We need the designing of FinFET actually. So
yes, FinFET you can design in QTCAD.
yeah, that is what I'm asking. If you, it will be helpful if you give a demo on that also.
Yes, I can arrange some demo.
Mm. Thank you.
So ma'am, for this FinFET technology, first we need to create the device structure, and that will be done by using the GMS technology. So here you can see, first we can define the technology, and then we need to create their 3D representation, and that will be done by the GMS technology. So for that you need some node point, meshing point, like you can see this is the GMS. So in this GMS, we need to design our device structure. So you can see I have generated some files. So for FinFET, I need to take some time so that I can create the device. As you can see, in this structure, we have multiple node points. So that node point we need to know, then we can design. So may I know any more questions?
No, my question was instead of showing us a gate all around FET or something like that, if you design a multi-gate FinFET or something, it will be more helpful for us. It will be easy to learn how to design multiple gate structures.
Like you can see, I have already shown you the GAFET, gate all around field effect transistor, that I have already designed. So you can see I have designed there.
You are showing
It
what
is
you have
present.
already designed. My intention is that if you show us how to design, it will be better for us.
Ma'am, for that you need to know their node point. So basically, their node point, their circle point, their meshing point. First, you need to know, then you can design. You can see we need to define all these parameters. Like this is the geometry, and this is the physical parameters, elementary entitles. So that we need to know, then we can design.
That you can give a demo now, no?
Yes, after I will take some time so that I can do the demo, because here we need to know the information there, input file. If I open this input file, you can see these are the mesh that I have created earlier. So this input parameter you should know, then you can design.
Yeah, my intention was that designing a gate all around is easy, but when you design like a FET with 2 gates or 3 gates, that will be more different from gate all around. No, so that was my question. If you just take a device structure and if you show us how to design it with different meshings, different dopings, how to construct different gates, that will be more helpful. That is my question.
Yes, ma'am. We can schedule some demos regarding that, and then we can give you, show you.
Okay, as of now, you can't show like in this demo.
Yes, 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 yes.
Okay, then we need to plan another demo if you have to show us how to design a multi-gate FET with multiple fins.
Okay, ma'am. No, okay. So regarding that, I will send you an email, and based on your convenient date and time, that time we can schedule
Yeah,
the
in
QTK
that
demos.
demo, let us make a device structure where we will be developing different multiple fins and multiple gate structures
Okay, okay, no,
with
okay, I will
proper
take.
dimensions and all, no, so that it will be helpful for us.
Okay, ma'am, no, okay. I think there are no queries for the NanoDCAL software. The query are regarding the QTCAD for the FinFET technology. So from my side, thank you so much for joining this presentation. And for this QTCAD demo, I will let you know.
Yeah, it will be helpful if you organize another session how to design FinFETs very soon.
Yes, yes, I will organize. Oh, yeah.
Yeah.
Okay.